So this last lesson, 7-9, all it does is really bring all of the factoring methods that we've been learning and practicing together kind of under one roof. So we've dealt with several methods individually. We started with GCF, that's going to be step one for anything. And then depending on how many terms, we saw there's different techniques. If there's trinomial, we're going to do magic numbers. If it's got 2 terms, we're going to look for difference of squares. If it has 4 terms, we're going to be factoring by grouping. So really all this says is it doesn't have any new methods necessarily in this particular lesson, but it does, just bring everything together in just like a mixed bag of tricks so that I can put any polynomial in front of you, and you should be able to, come up with a strategy essentially to how you're going to, factor it completely. So if we go through this, just to dissect this first sentence a little bit for our core concept, we want to be able to factor polynomials completely, and that means that we're always going to factor any GCF that is present in all of our terms. Okay, so any GCF. In fact, and we've talked a little bit about this before, I told you this was coming. This is one of the kind of prerequisites to being really truly factored, is if the leading coefficient is negative, factor that -1 out, right? So because I have been rolling that in, that shouldn't be a big deal for you now that we bring this all together, because I got you started on that fairly early. Anytime you saw a negative in the leading coefficient, go ahead and factor it out. It's really not considered fully factored if there's a negative leading coefficient embedded in your factors. It's also going to make your life easier now, number 2, when you're talking about end behavior of curves. I know that doesn't make a whole lot of meaning to you right now, but just trust me when I tell you, if the leading if the leading term is negative, factor -1 out. It's going to make your life a little bit easier for you. Then you're going to proceed to factor the polynomial based on the best method for the type of polynomial. And when we say the type, we mean the number of terms. And that's what we mean by that. So how you proceed after you pull GCFs, including -1s if necessary, how you proceed after that is really going to be dependent on the number of terms in your polynomial. So let's just review. For example, let's take a look at this first group. If you look at all of these examples here, all of these have 4 terms, okay? All of these are polynomials with 4 terms in them. And so if we go ahead and, review, when we're dealing with 4-term polynomial, of course, step 1 is always look for a GCF. But then once you do that and you factor that out, then we factor by grouping. That's our technique for this. So anytime you see 4 terms like this, you're going to factor by grouping. Okay? All right. So let's go ahead and get started and do a few, not all of them, but we'll do a few of these. Let's start with number 1. So we've got d squared plus 2c plus cd plus 2d. Okay? So none of those are like terms. The first thing I'm going to look for is there a GCF among all of those, something that they all share. But I think pretty quickly we can realize there isn't. Our leading coefficient is not positive. In fact, it's not really a leading coefficient in this particular problem, but that d squared, which would be our highest degree here, doesn't have a negative. And there's nothing else in common. So we're going to go ahead and proceed with factoring by grouping. So let's review that. We'll group the first 2, we'll group the last 2, and see if we can factor anything out. So what I want you to notice is right away, these guys don't, at least not the first parentheses. Okay, so the second parentheses has that d, which would leave me with a c plus 2, but the first one doesn't. So what I'm wondering is, could we maybe rearrange our terms a little, bit to help us with this grouping process? So if these groups don't seem to be working, and you see what I mean by that, right? If you look in the first one, there's nothing in common other than 1, right? And just so you see what I mean. And then this one does have a d, but when we pull that d, we're going to be left with c plus 2. So clearly not going to get a match there. So what we can do before we give up and say, hey, this does not factor, is perhaps reorganize these, okay? And, reorder things a little bit. So what I'm going to notice here is that perhaps I could put the 2's together, right? So maybe the d squared, maybe I could swap these guys out a little bit here, and put the cd next to the d squared, and then, this is going to be a 2d, and then put the 2c. So kind of group the 2 together, the ones that have the 2 at the end, And then let's see if, that makes a difference. If not, then this might not be factorable. But if we rearrange them a little bit, perhaps this does the trick. So I just swapped out those two terms. So the CV is in front and it's being grouped with the D squared. Here now I have a GCF of D, and that leaves me with still one D and a C. So many letters. And then how about the next one? The GCF there is a 2, so I pull or factor out a 2, and that leaves me with a D plus a C. A little bit of shuffling around sometimes is necessary if our terms came in a weird order, especially if it's not all in one variable. But, check that. Sometimes they don't factor, but if you check it and maybe rearrange things a little bit a couple of times, you might find that you get the right order, so you can do the factoring by grouping. And so now we do have those matching D plus C's. So our factors are D plus C, and then the other factor is the D plus 2. And there it is. And how do I know I'm done? Well, I have factored the original. There was no GCF, so we're still okay with that. So what I'm doing is I'm checking in each of these parentheses, right? This is really important. I'm going to be bluntly honest. Always check this on the test, or you'll get a few problems wrong. Make sure that when you look at these two terms right here, they truly and genuinely don't have anything in common, and they're not a difference of perfect squares. I'm going to check here. Are these two genuinely, factored and don't have anything in common? And make sure it's not a difference of perfect squares. When you have binomials, you'll always need to check for that. And make sure that you don't have any difference of squares that you could factor further. And then if you don't, then you can, safely say, okay, yeah, this is fully factored. And if you do have the time, you can always FOIL this quickly back in and make sure you do get those original products. Okay? All right, let's jump down. Let's actually jump down to number 3, which I think also is a little bit of a challenge. Just because, again, now this one is all in one variable. Everything is S's. So a really nice way to make sure we are setting ourselves up for success here is just to make sure it's in standard form before we proceed. So if we go ahead and rewrite this, here's my degree 3 term. I'm going to put that 64s squared next, then the positive s, then the 8. Okay, so that it is in standard form, going from highest degree to lowest degree. And that's really going to make it a lot easier, or more likely for me to be able to then factor by grouping, because I still have 4 terms. So I'm going to group these guys, I'm going to group those. And now that I've changed the order, I think this will work out nicely. And this first one, our GCF is an 8 and an s squared. Okay, we got both of those. All right, and then in this next one, in the parentheses, we're left with just an s minus 8. Okay. All right, and then let's take a look at the next parenthesis, or group, sorry. In this one, there's nothing but a 1, right? So normally we don't care about GCF of 1, but when we're factoring by grouping, we want to write that in front, because it's going to be one of our binomials. So yes, just 1 is the only thing that s and negative 8 have in common. Do we have a group match? Yes, we do. So then we can conclude our factors here are s minus 8, and in the other one, it is 8s squared plus 1. And those are my 2 binomials. Check to make sure there's no GCF, that s minus 8 doesn't have anything in common that you forgot to pull out, that 8s squared plus 1 doesn't have anything in common that you can pull out, and then make sure that neither of those are a difference of squares. And if they're not, then you're good. All right? You can always FOIL it back in to make sure it's not, it equals the original, and if so, then we're in business. Okay? The main thing here is, guys, every problem, this is unlike any other subject usually, but in this problem, when you're taking this test or you're doing this, you don't have to wait till Ms. Yoreda or any of your teachers check your answer. You know when you turn it in, you have the ability to check and know, did I do that right or not? Okay, that's a unique advantage that I think a lot of you guys could take more advantage of, right? Is to say, hey, not just be like, oh, I hope that's the right answer. No, actually, you could check right now and know exactly if that is the right answer. Okay, so take advantage of that. If you have the time, you have 2 days for this test. That'll give you plenty of time so you can do things like that. All right, so if you are good on grouping, you can try numbers 2 or 4 and then check them against the answer key. Make sure that they're in standard form. Sometimes you have to rearrange, but then you should be able to factor by grouping if it's factorable. And if you can't, then that means it's not factorable, it's fine. All right, so that's factoring by grouping when you have 4 terms. Let's talk about when you have 2 terms, like numbers 5 and 6 here. If it is a binomial, so this is just a little reminder, let's write this down. So for binomials, we wrote the steps for 4 terms. We pulled GCF, we factored by. For a binomial, 2 terms, right? Step 1 is still always look for a GCF. This is particularly important with these guys. It's always important, but it's really important with these guys. Factor GCF, and then with the binomial guys, at least right now in algebra 1, the only thing you can check for other than a GCF is check, is it a difference of squares? Remember, if I write it down, you write it down. So is it a difference of perfect squares? Which is one of the special cases. Always be on the lookout. I'm telling you right now, I'm going to throw this curveball at you on the test. I want you to catch it. Okay? So let's take a look at, for example, number 5. Okay, that's a binomial, has 2 terms. Step 1, we still always look for a GCF. So I notice that 4c to the 3rd minus 4c have a GCF of 4 and a c. Okay? All right, so when I pull that, let's see what's going to be left in the parentheses. I'm going to be left with just a c squared in the first term, because the 4 is gone and one of those c's is gone. And then minus, and then 4c divided by itself is just a 1. So this is a really good example of what I'm trying to get you guys to see. When we looked at it originally, if we had just said, is that a difference of squares at the very beginning, our answer would have been no. Okay, because c to the 3rd is not a perfect square, c is not a perfect square. But that's because we haven't pulled a GCF out. There's a difference of squares hiding in there, and we don't see it yet because the GCF is kind of hiding it. But after we pull the 4c, that GCF from both of those terms, we reveal that what's left is c squared minus 1. And I want and need you to be able to see that and right away say, oh, I'm not done. This is a difference of perfect squares. C squared is a perfect square, and 1 is a perfect square. A lot of us forget that sometimes, but 1 is a perfect square. 1 times 1 is 1, right? So this binomial right here, guys, this right here factors further. And if you stop here, your answer is wrong, right? You have to be able to recognize that that's a difference of squares and keep going and realize, oh, that part right there is going to factor further, right? C squared minus 1 factors into c plus 1, which are the square roots of those, and c minus 1, right? So the square root of c squared is c, and the square root of 1 is 1, and we get 1 is a sum and 1 is a difference. And then we look at that and say, okay, am I really done? Or is either one of those another difference of squares? That sometimes happens, hint, hint, right? Or is there a GCF that I forgot? But I think we're pretty safe here. C plus 1 and c minus 1. Neither of those are perfect squares. We are fully factored here. Okay, let's take a look at number 6. So number 6 says 100x to the 4th minus 25x squared. Now this looks like, you're like, oh, yeah, I know that's a perfect square. I got a difference of squares, it's subtraction, it's got perfect squares in there. You're not wrong, but that doesn't mean you don't have to, you don't have to pull a GCF. Okay, so you still have to pull the GCF or it's not fully factored. So let's go ahead and pull that. So I know that 25 goes into 100 in itself, so that's our GCF. And I know I can pull an x squared out of here as well. So if I pull 25x squared out, we'll be left with a 4x squared in the first term minus 1. Okay? Now, the original was the difference of squares, but we still had to pull that GCF out. Notice that after pulling it, we still have that difference of squares in there. 4x squared is a perfect square, and so is 1. So this right here, this binomial factors further. The square root of 4x squared is 2x. And the square root of 1 is 1. So one of those factors is 2x plus 1. The other one is 2x minus 1. And we still have our GCF out in front. This is fully factored. If you have factored the 100 and the 25, you will get a difference of squares that will have a GCF still kind of embedded, kind of sprinkled in that you'll still have to pull, and it will be harder to do it later. So still always do GCF as your first step, then see what happens after that. Okay, this is our full answer. 2x plus 1 and 2x minus 1. They don't have anything in common we left behind, and they're not perfect square. Okay? So that's how we're going to tackle binomials. If we had pulled a GCF, and what's left is like, I don't know, x plus 5, right? That's not a difference of squares, then you're done. If it's not a difference of squares, then after you pull the GCF, you're finished. Okay? All right, let's try a couple of trinomials, right? So these are with trinomials. It really, let me write this down. So with three terms, step one is still pull the GCF, right? As always, and then use the magic numbers, right? The magic numbers method is what I call it. I don't know, might be a better name for it, but. All right, so let's try number 8, and then we'll solve a couple and we'll do a couple word problems. So number 8, is there a GCF, right? Step 1, no matter what, is there a GCF between 20, 22, and 12? So I know that 2 certainly goes into all of those. No variable GCF, so all I can pull is a 2. That makes things a little smaller and a little bit easier to work with here. So this is my new polynomial right here. Okay? And I still have three terms, right? So I pulled the GCF out, but I still have 3 terms. I also have a leading coefficient. I have a 10 there. So I have to use, the magic numbers and kind of do the slightly longer trinomial process. So I'm going to do 10 times negative 6 is negative 60. And I'm going to look for 2 factors of negative 60 that combine to 11. It's a negative, so there have to be a difference. And so I'm trying to think of 2 numbers that have a difference of 11. And I'm thinking it's going to be 15 and negative 4. I know those multiply to negative 60. And I know they combine to 11. So now what I'll do is I'll rewrite this trinomial, but I'm going to split that middle term up. I'm going to do 10b squared. I'm going to split this up into the 15p and the minus 4p we just came up with. And that way I kind of uncombined the middle terms, and now I have the 4 original. And because I have 4 terms, I'll factor by grouping. I'll group the first 2, I'll group the last 2, and look for a GCF just within those pairs. So in the first pair, our GCF is 5p. And that leaves me with 2p plus 3. And the second one, our GCF is a negative 2. That leaves me with 2p plus 3. So that means that one of our factors is 2p plus 3. The other factor is 5p minus 2. And do not forget the GCF you pulled, which is still part of the original polynomial. Right? So this is essentially the prime factorization. Just don't forget, if you did pull a GCF, it is still part of your answer, just like it was on the previous ones. Like these binomial ones, the 4c was still there, the 25x squared was still there. Same thing happens here, right? If I have to have the 2 for this product to still be equivalent to the very original that I was factoring, right? Those 2 things should be equivalent to each other. If I multiply at any point these 3 factors, I should still have that trinomial as a result, okay? So does that feel good? So we've done a few of those. That's a little more fresh in our mind. So I'm going to do that one. If you want to try number 9, you can check it against the answer key. Let's talk about then just rolling in the zero product property, right? So now we're solving the equation. Notice the other ones that factor that weren't equal to anything. You can't just make an equal sign appear magically from thin air and decide that you want to create an equation where there wasn't one. The other ones were not equations, they were expressions. They weren't equal to anything, we were just factoring. This does solve the equation, and it is equal to something, right? So, real quick review, when we're doing these, we want to make sure they're set equal to 0 first, and then we proceed with the same steps we were dealing with a moment ago. So, let's actually try number 12. So, let's look at number 12. So, is it equal to 0? Check. Is there a GCF? Yes. There is a GCF of c squared. So let's go ahead and pull that. Leaves us with a c squared minus 81. Okay? Equals 0. And then I'm done if it's a binomial unless that's a difference of squares. So the question is, the only other big thing I need to check for is c squared minus 81. Is that a difference of perfect squares? The answer is yes. So that factors further. So now I've got c squared, and I know this binomial factors into c plus 9 and c minus 9, because those are the square roots. Okay? Now that it's fully factored, I can use a zero product property to solve, right? So I've got a few factors here. I've got c squared, so the question is what would make that equal to 0? I've got c plus 9, what would make that be 0? and I've got c minus 9. So what would make that 0? That's what we're trying to solve. Well, even if I take the square root of here, the square root of 0 is just 0. So that's one solution. Here, if I subtract 9, c equals negative 9 is another solution. And this is, by the way, a repeated root since we had 2 of those. Let's write that down. Okay, there should be 0 times 0. Okay, or there's two c's in other words. And then the c minus 9, I would just add 9 on both sides, and it just would make that the solution. So I have solutions are 0, 0, negative 9, negative 9, and positive 9. So c is 0 is just a repeated root, but these are the solutions. Okay, so that's just bringing together that zero product property. Okay? Let's try number 14, because it's not equal to 0, and sometimes that makes us stress a little bit, so I just want to remind you, if it's not equal to 0, step number 1, like a life dependent on it, is set it equal to 0. Okay, so let's go ahead and move these guys over to the other side. We're going to move 16x to the other side by doing the opposite sign, and we're going to move the 48 as well, right? And so I'll move those guys over here, and unfortunately, that does not have a square. Unfortunately, nothing combines here. These are all different terms. So after I'm moving them, I'm going to end up with that x to the third plus that 3x squared, and then the 16 is just going to be right behind it, that negative 16x, and then the 48, which is going to kind of add, extend this polynomial because they were not like terms. So we just now have 4 terms on the left and nothing on the right. That's the important part. Okay? So I got x to the third, x squared, x, and 48. None of those are like terms. Okay? But it is equal to 0, so we can get started here. We have 1, 2, 3, 4 terms, so we're going to do the GCF first and then factor by grouping. Is there a GCF among all of our terms? No, right? Nothing numeric or variable. So then because we have 4 terms, we're going to use the factoring by grouping method here. Okay, the first one here has x squared as a GCF. And let's see, when we pull that, that's going to leave us with x plus 3. Okay? So far, so good. How about over here? Negative 16x minus 48. The GCF, there is a negative 16. I'm able to pull that whole thing out. And when we do that, it's going to leave me a positive x. And then negative 48 divided by a negative 16 is a positive 3. So this worked out nicely because we have our matching binomial in. So one of our factors is x plus 3, and the other factor is x squared minus 16. Okay? And we did our factor by grouping, and we did everything right. And if you box this as your final answer, you're wrong. Right? Hopefully you're seeing it already, but this is not completed. Okay? This is an example I was telling you, and like I said, I'm going to be blunt, and there's going to be stuff like this on the test. So after you have factor by grouping, and we did that perfectly and beautifully, we need to make sure that our binomials are really at the end of the road, that this really is at the finish line, okay, that there's no GCF, and that neither of these are a difference of squares. And so if you're paying attention, you have to realize, ding, 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 that's a difference of squares. That's a difference of 2 perfect squares, and that factors further. We are not finished, okay? You have to be able to spot that, know it, and then finish this out. So this really factors to x plus 4, x minus 4, and so the full factorization that is really done is right here, okay? Those are all factored, they don't have a GCF, and none of those are the difference of 2 perfect squares. Now we're finished. Okay, so be careful and make sure you always check for that in your binomials, even if you think you're done. All right, so let's finish out with number 15 here. It says a jewelry box in the shape of a rectangular prism has a volume of 96 cubic inches. The box has a width of x inches, a length of x plus 8, and a height of x minus 2. So if it helps, go ahead and draw a picture. You know that I always think that's really helpful. But the main thing here, my boxes, I've done better. I've done a lot better. But that's okay. So it tells you that it has a width of x, a length of x plus 8, and a height of x minus 2. Find the length, width, and height of the jewelry box. So because they give us a volume in 3 dimensions, for a rectangular prism, we know that that volume is just the product of all 3 of those dimensions. So if I multiply all 3 of those together, that's how we get the volume. So if I multiply the 3 dimensions, it's the x times that x plus 8 times that x minus 2. When I multiply all of that together, it turns out that resulting volume was 96. So that's our original setup. But if it's not equal to 0, then these factors are not going to be helpful. We're going to have to multiply this together. So maybe I'll FOIL these. You can do this multiplication in any order. I like to FOIL first, then distribute the x, but you decide. Okay, and when I FOIL that, I'm going to get an x squared plus a 6x minus a 16. Okay. So once that, that's first order, inner, last, and then combining the middle term. So that we get that trinomial right there, and then we still have to multiply by that width, so we distribute the x. So then we get x to the third plus 6x squared minus 16x is equal to 96. Okay, so we're getting closer. Now we invite the 96 over to the left so that we can set this equal to 0. And our new one is x to the third plus 6x squared minus the 16x, and then minus the 96 with nothing on the other side. Okay, so we move the 96 over. We now have 4 terms on the left, and this is equal to 0. And when we have 4 terms, and it's equal to 0, then we just factor by grouping. So we'll group the first 2, we'll group the last 2. That's going to leave us an x squared right here, and x plus 6 in the parentheses. And the second one will have a negative 16, so I know that goes into both of those. And that gives me an x, and then negative 96 divided by a negative 16 is a positive 6. Okay, so I'm going to come up this way. So our 2 factors are x plus 6 and x squared minus 16, and that's equal to 0. But again, I want you to understand that still factors further. I want you to see that x squared minus 16, catch it, know it, recognize it, and factor it further. So that really factors to this. Okay, and then we can find our zeros to kind of see what options we have. So we set each one of these equal to 0. One option is when x plus 6 is equal to 0, which would make x be a negative 6. Another option is when x plus 4 is equal to 0, which would mean x would be negative 4. And the other option is when x minus 4 is equal to 0, which would mean x would be a positive 4. These all mathematically work in the polynomial, but the question is, if x is representing the width of our box, a jewelry box, are all of these an option? And the answer, of course, is no. You cannot have a jewelry box with negative 6-inch width or a negative 4-inch width. It has to be 4 inches. Okay, so that tells us here that our width, which was just x, is 4 inches. Our length, which is x plus 8, that's 4 plus 8, is 12 inches. And the height, which was x minus 2, 4 minus 2 is 2, is 2 inches. So these are the dimensions of your box. All right, so we're going to stop here, and then tomorrow when you get to class, we're going to talk about 16 and the graph problems.